All right, welcome everybody to week 13, day 1. There's a humble bundle right now on the secrets of game design, and so $18. I'm probably going to pick this up and kind of go through it a little bit, and so maybe over the next couple weeks we can talk more about game design, stuff like that. Seems like a pretty interesting collection of books. The philosophy for understanding games. I think one of them was like a magic system one. Yeah, Game Magic, a designer's game to magic systems in theory and practice. Sounds kind of fun. How to design magic systems for games is kind of interesting. I got my own ideas on the subject, but I'm curious to see what they say. Incredible iPhone and iPad games and the stories behind them. See, that I don't know about, because I actually have this theory right now that there's never actually been a good mobile game. I'm sorry. I know they made a lot of money, but like I don't think there have been any great or incredible mobile games ever. I'm just gonna, that's my thesis. I'm gonna throw that out right now. Like Angry Birds, sure, it's a fun little puzzle game. Is it an incredible game? No, it's not. It's just a really simple little janky thing. You hit the thing and they explode and they fall over, and it's fun. I wouldn't say incredible. Incredible is way too, like Fruit Ninja. Like is that incredible? I would argue no. I would say it's not an incredible game. Words with Friends. We made Scrabble, but online. Like, okay, So, could you post a link to it? Yeah. Yeah, sure. And so we're probably gonna I'll probably assign you guys something like that. Don't buy it just yet, Dalin. So, you'll have to get a copy of one of these PDFs and read a little bit and do a little presentation on it. I think there's a lot of good things in here. This one I'm a little bit dubious of, but who knows? Maybe I'm open to having my mind changed. Maybe there's some incredible iPhone game that I have simply never played. I don't know. So I'll take a look at that. So we'll probably give you guys one of these things as an assignment, and it should be fun. It's always fun to read about games and really discuss them kind of academically. It's called Ludology, right? The academic discussion of games is called Ludology. Right? So an analytical discussion of gaming. What is Ludology? It's understand games. Okay. So you can get a doctorate in ludology if you want. So, what are you? I'm a ludologist. I'm a member of the International Society of Ludologists. Yeah. Okay. So we'll talk more about that later. So our topic for today, and it's going to be a short topic. Last time we did a little half hour on how rendering works. And I'm actually kind of proud that we kind of went through the whole rendering pipeline in about half an hour. The background, by the way, is from Dune. And you can see the spices shipped, and it's got a reference to Tuick, who's one of the smugglers and things like that in there. So I watched the movie. Pretty good. I liked it. I'm looking forward to the second part. I have a couple issues with it. Like, why did they shoot a las gun at Duncan, Idaho as he's flying off in his Thopter? His Thopter was shielded. And they were shooting at it with a las gun. Like, what the hell? Like, that doesn't make any sense. If the las gun had hit his Thopter, it would have created a nuclear explosion that would have destroyed all of Arakeen. And it would have taken out the ship that was shooting it. Like, there's no person in the right mind that would have done an orbital bombardment with a shield on somebody who is clearly shielded. Like, it just doesn't make sense. Anyway, that's my one quibble. That, and the fact, obviously, there's more to the movie, but you can't really complain. It's already pretty long. So. All right, so today we are going to talk about ray tracing. And the way ray tracing works is very different from how rasterization works. So with rasterization, you've got a world full of triangles, and you're trying to draw them to the screen. And if you have a bunch of triangles, like a lot of triangles, they can all overlap. Like, you got a triangle out there in the world, and basically what you do is, actually, this is ray tracing. This isn't right. Well, whatever. There's some sort of rule for like how you colorize pixels, but basically you kind of fill all of the points inside of the triangle using the line scan method, and the color that you do, you interpolate using barycentric coordinates. Is what we talked about last time. Barycentric coordinates is basically how close am I to the blue edge or the blue vertex or the red vertex or the green vertex. And you compute that using some cross products and things like that we talked about last time. So with ray tracing, it's different. And because the problem with rasterization is that if you have a lot of overdraw, if you have a world that's very, very complicated, and you've got, I don't know what this is, but you can see here, you got all these buildings, and they're all overlapping each other, right? And if you don't have a good acceleration structure, if you don't have a good structure that will allow you to quickly occlude things and eliminate them from being drawn, then what's going to happen is that look at that. That is just, look at that texture. It's amazing. What's going to happen is that it's going to draw the triangles for this building, and this building are going to draw on top of it, and this building is going to draw on top of it. So you have the same spot on the screen actually being overdrawn over and over again. And as we talked about last time, there's actually one of the fundamental limits on how many frames per second you can get is the fill rate, how many pixels can be pushed to the screen per second. And even though like my 3090 has a pretty good fill rate, if you have a lot of overdraw, if you have a lot of triangles that's drawing the same spot on the screen over and over again, you can very quickly have your frame rate dip, right, below the 60 or nowadays. I kind of like having like a 98 hertz refresh at 4K ultra resolution. That's what I'm looking for in a game. But 60s is still acceptable. I played Witcher 3 ultra 4K resolution at about 60 to 70, I think, on my system right now, and that's acceptable. So ray tracing works differently. Okay, so imagine you got this scene here, right? So with rasterization, what you do, the algorithm works like this: for every triangle on the screen, rasterize it. Okay, so for every triangle you have in the world, the more triangles you have in the world, the more work you do. And by in the world, I mean within your view frustum. Right, so you got your camera here, it's got a near clipping plane, a far clipping plane, field of view. All the triangles within that view frustum, you have to rasterize to the screen if you don't have some sort of occlusion system in place. And so the more and more complicated the world gets, the slower your game runs. Right? Are you guys familiar with this concept? Like, you keep adding more and more stuff to your game, and the frame rate starts tanking slower and slower. You guys know what I'm talking about? Aaron, Dolan, Betancourt. So, the difference between rasterization and ray tracing is that rather than operating on a per triangle basis in the world, which means the more triangles you have, the slower you are. With ray tracing, you operate on a per pixel basis, or per fragment basis, again, if we want to be technical. So for every pixel I have on the screen in the world, what I do is I shoot a ray out of that pixel, and I see what geometry I hit. And typically, you can find the geometry that ray is going to hit in an order log base n time. So essentially, not quite free, and it does go up slightly the more objects you have in the world, but for every doubling of the objects in the world, you only have to do one more operation. And so that's pretty good, right? So if you have a million objects, a million triangles in the world, you can find which triangle the ray hits in about 20 steps. That's pretty good. And so the cost of ray tracing goes up with the number of pixels you have on the screen. But, if you have a 4K screen, when you're rasterizing, you're still going to be outputting all those pixels to the screen once anyway. So it's not too bad. And so you can actually have a very, very complicated world, and your ray tracing algorithm can actually be faster, which is not something we normally think about. Because if you think about like ray tracing, raw tracing, the Egyptian version of it, if you think about ray tracing for like Pixar or something like that, something like that. So this would be like a ray traced image. These things oftentimes take like 8 hours to make, and that's obviously not good enough for a video game. But it's really nice because what happens is you shoot a ray out, and it can actually reflect off the shiny surfaces and things like that. And so the reason why ray tracing takes a long time usually is because instead of just sending 1 ray per pixel, they'll send 10 or 20 or 100 or 1,000. If you're Pixar and you're making a movie, you really want to get it right. You know, you don't want to have like some low quality, fuzzy kind of thing. You can do that to kind of like preview the world. But this is why, like, when you play RTX enabled games, there's usually ray tracing low, ray tracing mid, ray tracing high, ray tracing ultra, and that basically just controls the number of rays per pixel that you send out. But by default, like if you just want a really simple render, especially on a world like this one, you know, where there's not really any reflective surfaces or anything, you can actually probably render this entire world with just 1 ray per pixel. So you send a ray out from this pixel on the screen here, and it flies forward and it hits the church. Okay, what's the color there? And there's a triangle there, and you're like, okay, well, this one's textured with a stone texture, so it's gray. And then you send a ray out from the screen to the pixel next to it. Well, that's the crack on the brick, so it's black. And you just do that one, you know, you could just do 1 ray per pixel on the screen, and, you know, you hit the grass over here. What's that color? Green. Cool. And this thing is not lit. It's not reflective. So you can actually run this scene here in ray trace mode probably faster than you could if you were doing rasterization. And that's weird, because we're used to ray tracing being this like really slow, expensive thing, and rasterization being faster. But in reality, in a really complicated world, if you just send out 1 ray per pixel, ray tracing is actually going to be faster, which is a weird concept. Some Overwatch artists making Pixar level stuff, yeah. Are all those balls computer generated? Yeah, looks good, right? Yeah. So, but if you want to do artwork like this, this doesn't need to be real time. This doesn't need to be in a game. These things aren't moving around. So spend all night on it. You know, you're going to submit it to some art contest, right? You set up your 3D world. You know, you set the specular highlighting like on these things, and the shininess and the roughness. You have probably roughness in a normal map and all the other stuff. This is emissive. You can see this one's glowing. Yeah, no, that's CG. Here, I'll turn up the resolution too, so you can turn it up to 4K resolution. And yeah, and so what you do is you set up these are all, you see how they're like perfect spheres, like you kind of tell that they're artificial because these are glowing, you know, stuff like that. And so they're perfect spheres, except for this one, I guess. They didn't do a displacement map, which would actually move the vertices around. So even though there's like divots and things like that on them, you can see it on the profile, they're actually perfect circles. So that's a good way to tell something's a CG. So what happens when you do something like this is that they'll spend 8 hours, 10 hours rendering a single frame. In fact, with Pixar, they would set up all their animations for the night and they would go home. And then in the morning, they would come in and check, okay, cool, we got another second of the movie done, you know, because they would have these huge rendering farms. And they would set up their animation for the next 3 seconds of Buzz Lightyear doing something. And then, you know, they spend all day doing the animation and stuff like that. And they do like rough, low-res previews. They can kind of see that everything's in the right place. And they do a higher res, and then a higher res. Like, all right, it looks pretty good. All right, let's do this. And they hit it, and they go home from the night. They come back in the morning. All night long, these machines are just rendering like a second of the movie. And then after, you know, a couple of years, they have an entire movie. And boy, do you hope that you don't have to make any script changes at that point. You know, you know, it turns out that Buzz Aldrin, the namesake of Buzz Lightyear, if he, you know, got canceled by saying something racist or something, you know, then you'd have to go through and redo all the, yeah, man, oof, you know. So that's how people typically think of ray tracing. We think of it as this really expensive, slow thing that's not suitable for games. But in reality, as long as you're willing to compromise on quality, on reflections, and things like that, like you can actually make ray trace games actually run reasonably quickly. So what happens here is that, let's say you send out a ray. Let's say we're sending out a ray to this point right there, where my mouse is. You send out a ray, and you hit a surface. Okay, just one ray, that's fine. Now, you discover that it's reflective. See, on that village before, nothing was reflective, so it's very easy. Like, you're done, you know? Is there any lighting? No, it's all flat lit. You know? Okay, we're done. You know, what is it? It's green. Okay, it's a green pixel. Draw it on the screen, you know? Here, though, we've got lighting. We've got 1, 2, 3 emissive marbles in the bunch. We've got, it looks like back behind the camera, we've got a light shining down on the surface, like kind of like right here, shining on the surface. You can see the reflections of the light. You know, it's not a physical light, like you can't see a lamp or anything. It's literally just a point light. And then it looks like they've created 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12... 13, 14, 15 more point lights that are less bright in the area up here to kind of help illuminate it. So you got about, let's say, 20 lights total in the scene. So what happens is that when the ray hits that point there, then it shoots what's called a shadow ray. So let's say it hits right here. What it's going to do, it's going to shoot a shadow ray from that point towards every light in the scene. Because it's like, I want to know if I can see that light. And so like, if you hit right here, it's going to shoot a shadow ray from that point to the main light here. And it's like, yep, you can see it. And then based on the angle of reflection, like there's physics, there's Snell's law for refraction and all this stuff. You know, basically based on the angle coming in, the angle coming out, yes, that's going to be light. And you're going to draw whatever the color of the light is, in this case, kind of like a warm yellow color, right? And then, but you're also going to do it for all the other lights. So like if we hit here, it's going to shoot shadow rays to each of those 20 lights in the scene. And like maybe the ray coming from here to here is blocked. Do you guys see that? So like if you hit here, it's going to say, hey, can I see that light over there? Nope, there's a marble in the way. So it doesn't get any light from that one. And it's going to shoot a shadow ray to this one. Can you see that one? Yep. And so you can see this area here is lit from that glowy marble there. And it shoots a ray down here. And it's like, oh, there's something pink there. So it picks up some pink for these things down here, and it hits these guys down here. That one's blue. And you might be like, well, how do you know it's blue? Well, you got to shoot more rays off. So every time you hit something, you scatter more rays. And then those things hit things, and they scatter more rays. And that's why it can take forever. Because how many, like if you set up, have you guys ever been in like my upstairs bathroom area, there's a mirror on one side, and there's a mirror on the other side. And so when you look into it, it's like the infinite. You guys ever seen that? Like the infinite mirror effect? Right? There's just infinite reflections back and forth, and there's like 9 million copies of you, you know, stretching off into forever. So, how do you handle that in ray tracing? You know, you like wave at yourself. 9 million of you wave back. So when you're doing ray tracing, that's not a solvable problem. It's an infinite loop, you know. And so at a certain point you have to cut it off. You're like, all right, we've done 20 reflections, now we're done, you know, kind of thing. So there's a quality level. And so whenever you do ray tracing, there's kind of a limit to how many reflections you pick up. And so what's happening like here is that we send a ray here, and then it's going to scatter light, shadow rays towards all the lights, but it's also going to reflect off, and it's going to hit this person here. And then this person, it's like, well, I need to know if that point's lit, and it's going to shoot off shadow rays to the different lights, and it's going to reflect off, and it's going to reflect off, and it's going to reflect off. And that's why you can sit there and run this thing for 8 hours, because you just keep bouncing. You hit, you scatter 5 more rays. You hit, scatter 10 more rays, and you average the results together. Okay, I'm blue. You know, okay, well, if I'm blue, then me, who sees you, I'm going to reflect some blue. You know, I'm pink. Okay, cool. So I just shot a ray at you, and we scattered around. We figured out you're pink. Okay, cool. So I'm going to add pink to me. And then all this gets summed and averaged together, and you end up with a single pixel value at every point on the screen. You guys understand? Stack Overflow, yeah, exactly. Infinite recursion. So you can, you know, if you don't have anything reflective or refractive or lit, ray tracing is simple. It gets hard when you've got reflections, you know. And so when you have a shiny surface, you're not just done when you hit it. You're not just done when you do the shadow rays and you figure out if it's lit or not. It's now got to bounce off, and oftentimes it bounces off multiple rays in slightly different directions. and then it has to average together the pixels on those. So if it hits here and it bounces off in this direction, it's going to maybe cast a dozen rays over here, and it's going to average them all together and be like pink. Okay, so we are seeing pink in that direction, and we are like 50% reflective, so it's going to be 50% my color, which is like this pewter color, and it's going to be 50% pink. And then there's an averaging process, and then the result reported back to the original ray coming out of the camera. It's going to be like 50% pewter, 50% pink. So, yeah, you can just let these things run forever if you want, and it will just keep getting more and more accurate. This is not useful for game development, though. For game development, there's a lot of tricks we do. Like we can defer some of the extra work. So like if every frame, like if our camera is not moving, then every frame we can just kind of do more random ray traces and things like that, and learn like, okay, so we bounce here, 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 and you'll actually see in ray trace global illumination things. That's Tristan. Yeah. Let's see if we can see it. Unfortunately, the tech demo for global illumination doesn't work in the latest version of Unreal Engine. They actually kind of broke it, I think. So what would happen is
remarkably intuitive way in the much less computation.
Okay. So what you'll see, if as long as the camera is sitting there, you'll actually see the shadows. There will be like some noise in the shadows, and it starts like fading away as the system is sort of figuring out where things are lit and where things are not lit. So there's a
to have a look at that.
See if we can see any evidence of this. There's usually like shimmering in the shadows when you see like a ray traced. This is too good. Let's see if we can. Let's see if we can find the shimmering. Oh, that's the general idea anyway. I would show you, except it doesn't work anymore in Unreal Engine. So, okay. So yeah. So with global illumination, you're basically trying to solve a very complicated problem. The complicated problem is like, let's say you got a room, and actually, should do this quick too. Why global illumination is so demanding, yeah. So yeah, like when the light gets blocked, like the whole world needs to update based on that. Let's see if I can just find a screenshot of this. There's some good talks on how the Quake 2 global illumination worked. Yeah, okay. So you can play it. You know, this must be old. Yeah, it's old. Just give me a screenshot. I just want a screenshot. Okay. So here's one of the scenes from the talk that I watched, and it's a really good talk if you're interested in how all this kind of stuff works. And basically, you've got a problem. You've got this room. It's kind of dark. It's got some emissive surfaces over here. These things are shining lights out, and you can create what's called a light map, where like normally when you pre-render a world, you can kind of figure out, okay, here's all the lights in the world, and here's objects, and here's where the shadows are going to be. So the standard way of rendering the scene, this is probably actually maybe from the original Quake 2, is you've got these sources of lights, and I think there's maybe some lights in there that probably don't contribute much. And then you can basically say, okay, this spot here is not lit by you, and you probably put a light out here, and it's probably a little bit from that one. So you guys see how the shadows are? So these are like pre-computed shadows. And then you don't have to compute the shadows in real time. You just use the light map. And if you're doing a stealth game, then you would have the ability for the engine to pick up the light map of the surface you're sitting on. So typically, your stealth level is actually based on the shadow on the floor, not the shadow at chest level, because it just grabs the shadow information off the spot you're standing on, which sometimes creates some rather hilarious, effects where you can hide right in front of somebody. There's a table like this big, but because the table casts a shadow on the ground, you're hidden, in it. Do you guys know what I'm talking about with like a shadow map, like a light map, where you can like pre-compute these things? You guys understand? Like you basically just have a surface here, and the surface has written into it like, a light map. Okay. Light pollution map, no. So like if you have fixed lights and fixed geometry, you can pre-compute which areas are in shadow. You just basically go through every point on the surface here, and you basically say, can I see the light? Nope. Okay, it's in shadow. And so you actually can save this to disk. It's like how you have a texture. A texture is like a picture on the world. You basically have a shadow map or a light map that that holds how much lighting there is in the static world. And Unreal Engine does this. Every time it says pre-compute lighting, remember, and you like, warning, something's moved, and it has that annoying message in the top left corner of the screen. You guys know what I'm talking about? And you like rebuild lighting. That's what it's doing. You guys remember that? Like the little annoying message that's always up in the top of the screen? Yeah. So what it's doing, it looks at all the lights in the world, it looks at all the geometry in the world, and it saves to disk basically a picture of the shadows, if you want to think of it that way. And then when you play the game, the shadows are there. It doesn't have to dynamically do all this. Like, you know how long it takes, right? So it doesn't have to do that in real time. It just pre-computes them. So this is probably the original. Okay. So then this shows you what I think from the talk, and don't quote me on this, I think this was their first pass at trying to do a global illumination with ray tracing. And so you can see here, actually, the emissive surfaces aren't emitting lights anymore, because if they were, there'd be a shadow coming this way. Or maybe the first one was just the emissive textures, and this one's the lighting. Either way. So you can see here they put a very strong light outside, and they put in some haze in the air. And so the haze will scatter light volumetrically, so you have volumetric fog basically here, which looks really nice. You can see there's like kind of a Jesus beam coming down right here, right? God beam coming down. And Cropuscular Lighting is the politically correct way of referring to that. So you see that right there. And looks nice. You got that in, but then this isn't doing anything. And then here, let's see what we got here. Interesting. Oh, it's time of day. That's a different time of day. I see. And so the challenge is, if you have all this light over here, it wouldn't make sense for this area over here to be pitch black. You know what I mean? So like, let's say there's no emissive lighting, and you just have this big area over here that's like illuminated. This is like noon or something, right? It would not make any sense at all for this to be black. Even though there's no line of sight from the sun to here, by default, it would just be black, right? For 48,000. Yeah, exactly. So what we typically do in a video game is we add ambient lighting. So we'll just basically say this room has 30% lighting on everything just because there's a door and a hole in the roof and things like that. We'll just add a little bit of lighting to everything. With ray tracing, you can actually have light reflect around naturally. So you can have all the light over here contribute light to this and contribute light to this. And so it's a problem called global illumination. Like, so you can have an area of intense light and it's going to reflect around and sort of bathe the light in sort of a natural illumination from this beam of light coming in. It's a really beautiful effect when you pull it off. It's also very computationally expensive. And so typically they'll do like this temporal averaging over time. And that's why I said you'll sometimes see the shadows shimmering and fade away as it sort of figures out that there's a bounce path from here to the back of the thing over here. You'll see the shadows kind of shimmer and adjust over time. And it's quite a nice look. Click to load an RTX on versus RTX off. Okay, cool. All right, so RTX on, RTX off, RTX on, RTX off. So here you can see it's just ambient lit. So they just have some sort of like flat lighting on everything, so it's not black. You know, these things over here are just glowing because they're power-ups. They just want to make sure you see it. That is completely opaque. The water texture is opaque. These things are completely flat. Even the bolts or whatever on the surface are completely flat. There's no bump mapping on it. You can see right here it's completely flat. And then here you can see they added a bump texture. So it's actually a hole, which is kind of an interesting take. I wouldn't have done those with holes, but they added a little bit of a bump texture to that so that there's a little bit of 3D on it. The water is now transparent. You see the difference in the water. The water is now transparent. It's reflective. So it's got reflections coming off it because it's ray tracing, right? When you hit a water surface, when the ray comes out and hits a water surface, it's going to cast a reflection ray up this way, and it's going to cast a refraction ray down this way, and possibly multiple ones, right, depending on your quality settings. And so what you do with ray tracing is when you hit a reflective or refractive surface, well, let's go. Let's do this. And what your RTX card does is it accelerates that whole process for you. And so you basically just say cast this number of rays out, and then it handles in hardware all these things of like, what did I hit? Okay, it's reflective. Okay, recast, average together, things like that. And that's why RTX video cards are so cool. It's because it'll speed up this whole process for you. And then you got some volumetric fog up in here. These things no longer glow. The walls have obviously higher resolution textures. The water looks really nice now. And you've got actual lighting coming in. And the lighting is kind of bouncing around, and areas that are directly lit are lit, and areas that are kind of picking up indirect bounce lighting are darker. Right? Whereas before, everything is just the same. You see that? Flat lit. So global illumination is quite a beautiful look. Let's see if they can... So this is the original. It's kind of dark and gloomy, and then here it actually changes the mood of it quite dramatically, right? So here it's all dark and gloomy and red, and this is actually one of the architectural features of Quake 2, which is they added colored lighting. Quake 1 didn't support colored lighting. I think maybe one of the expansion packs for Quake 1 added support for colored lighting, but Quake 2 added colored lighting. And so this was like a tech demo from 1997 or something, showing, look, we can have red colors. Oh, how amazing. You know, and then they did this. And so you've got an opening to the sky. You've got sky beams coming in that are directly lit by the sun, and then the rays bounce around. And the more rays that bounce around from the sunbeams that hit surfaces, the more they get lit. And so you can see the area out here, it's subtly darker, right? Because there's less paths that bounce around to get out here than there are that can bounce around inside of here, right? Just imagine randomly scattering rays from these sunbeams, and it creates a very subtle, that nice soft shadow on that thing there. You know, whereas before, what shadow? It's you know, it's all shadow. Who knows? You know, there's no, you know, they did a you can see the pre-computed lighting here, right? They put a red light up here and a red light up here, and so it basically did a shadow map. It says, okay, is this spot visible to that light? Nope, it's in shadow. And then they added a little bit of ambient lighting, darker ambient lighting, so you can see things, because pitch black is hard to play a game, you know. But here you can see there's no they probably took out the red lights entirely and opened it up to the sky, and so there's no directional lighting over here at all. It's interesting. Original, RTX on, RTX off, RTX on, RTX off, RTX on, RTX off. So, yeah, they added emissive lights over here. You can see the shadows over here. There's no, they didn't even pre-compute shadows on that one over here. So, yeah, really cool stuff. Yeah, just really, you know, and this is an old game, and you can see that the monsters and things like that are still like kind of, you know, lame looking, and you know, like the you know, it's still not like a modern looking video game, but like, you know, all this like global illumination and you know, ray tracing and refraction and reflection type stuff. It's a neat look. It's a really neat look. And you can see here the cost of global illumination, right? So with no global illumination, it goes from 90 frames per second to 70, turning on low global illumination. Medium drops from 90 to 60. High drops from 90 to 55. So it's a fairly substantial cost to do this. But it looks nice. It looks really nice. Creates, you know, this is a 20-something-year-old game, 24-year-old game. It looks nice. Just adding a little bit of ray tracing to it, you know? Well, it's more than that. Like, they actually did a lot to do this. And if I can find the talk on it, I'll post it. It's, yeah, it's actually probably useful. Okay. So, yeah, so this is how it works. So when you shoot a ray, everything in the world is held in what's called BVH format. We've talked about this before. They're basically axis-aligned bounding boxes, I believe. They're not oriented bounding boxes. And basically, what it accelerates is the ability to draw a line and find what you hit quickly. Okay, so you got some sort of structure, data structure, BVH, that gets loaded into the graphics card. And so the graphics card has to know all of the geometry on the screen. And it has to have a BVH for the entire scene geometry, and then when you shoot a ray out, it will very quickly tell you that ray hit the eye of the rabbit or whatever. And then, so you set up a BVH, you then can very quickly do that, and then, like I said, you scatter rays. And what you'll get though is, because it's random, like sometimes it'll scatter and hit a light surface, sometimes it'll scatter and hit a dark surface, and it's random. And so what happens is you get a noisy sort of approximation of like how much light there is at that pixel, and then they run what's called a denoising filter on it, and it goes from this into something that looks like this. But if you look really carefully at the shadows, you'll see them kind of flickering, and then over time, as it gathers more information, you'll see them kind of settle down and stuff. But if the lights move, then you'll see the shadow's kind of doing this flickering thing again. Oh yeah, I've looked at this before. This is kind of cool. So, so rendering one frame of Metro Exodus, which is a game that Hike, I think, likes. So it's using all 32-point floating point cores. Takes that much time. Then on 2080, not using any of the ray tracing stuff, it's got a bunch of 32-bit integer cores, and so some of the math can be done in 32-bit ints instead of 32-bit floats. And so by having extra compute cores, it can overlap some of that work. And then the ray tracing cores can be used to offload like the lighting calculations or whatever it is they're using it for. They're obviously not using them for the whole frame, but you don't have to use ray tracing for everything in your scene. You can actually just use it for just global illumination or something like that. So you can kind of layer ray tracing on top of other things. You can see by doing that, it was able to accelerate this whole chunk of code here which is probably the lighting code, got smushed down into that little bit right there. So it actually was able to speed up rendering time quite a bit. So Metro Exodus uses global illumination and ambient occlusion. So ambient occlusion is self-shadowing. So like it's used a lot for noses and things like that. Basically, you want to know how much is a shadow, how much does an object cast shadows on itself? Like if my hand is casting a shadow on my face and things like that. Now it's a moving hand, so it wouldn't be used exactly. But if you have a static mesh, you can kind of figure out which areas of a static mesh shadow which other parts of the static mesh. And they typically do so by hitting a point with a ray, and then you randomly cast rays in different directions and see what percentage of those rays are occluded. So in this case, it looks like this chunk from here to here is occluded, and these areas are open. And so it saves them into what's called an Ambient Occlusion Map, and it writes down basically these areas down here. If you cast rays out, they hit solid things, but the area on top here doesn't hit anything. And then you can use that Ambient Occlusion Map in conjunction with other lighting techniques to create self-shadowed lighting that looks pretty good. And there's a lot of different ways of doing this. If you've ever seen anything like SSAO, HBAO, I've seen those a lot in video games. And yeah, so this is what it looks like. So basically at every point, like the area under the hat, what happens is that at that point, it shoots out rays in a hemisphere, and most of them get blocked. And so it makes it black. And then the areas where it shoots out things and doesn't hit anything, like the end of a nose, right, it'll go outwards and not hit anything, then that's white. And so by just layering this ambient occlusion map on top of the other lighting, it creates nice looking shadows and things like that. So the areas in the little crease of the tank there, they get blocked by everything. The tip of the barrel obviously goes off and doesn't hit anything. So, and it'll shoot it for like a limited distance. It's not like this person's going to be blocking the tank. You know, they go out for like a meter or something like that. I don't know. I don't remember off the top of my head. Okay. Let's see here. Reflections, yeah. So you can, when you hit something, you can see what it reflects off of and hits. So you don't have to use all of these techniques for everything, right? You can pick and choose. Caustics is the light pattern. Like if you've ever gone to a pool, you know, like there's that pattern on a pool, like the light pattern on a pool. Yeah, like that. Right. You guys have seen that before? They're called caustics. I learned that from actually the guy who made Team Fortress, so Robin Walker. He told me that term. Kind of cool. When I met him at E3 a while ago. Yeah, so that's called caustics, and you can do that using ray tracing, right? So you shoot a bunch of rays and figure out where they hit and get caustics that way. So that is our class for today. Yeah, Battlefield 5 was the first game to launch with ray trace reflections, and Battlefield 5 was not a good game. It's not a good game. Yeah, I had a 2080 Ti and yeah, I had a 79. This is actually like my rig, except I had more RAM than this. I was running it at 4K resolution. So yeah, it run at about 40 frames a second. And with dynamic learning, this basically runs the game at 1080p and sharpens it up to 4K. You can get actually a reasonable frame rate, but the Battlefield 5 ray tracing implementation is quite buggy at launch, and I didn't play it long enough to see their refined implementations of it. Alright, so that's it for today. Hope you guys learned about ray tracing. Basically, you shoot a ray out from every point on the screen and see what you get. And there's all sorts of complexities and intricacies and things like that, but that's the basic idea. You just shoot one ray, or 10 rays, or 100 rays per pixel, and scatter them and kind of just see what happens. And I think in the future we're going to be moving more and more to ray traced engines, because it doesn't have that problem that triangles have. Triangles, the more triangles you have on the screen, the more triangles you have to draw and overlap and overlay on top of each other. And with ray tracing, the cost goes up with the logarithm of the number of triangles, not proportional to the number of triangles, and that's huge. And so once I think we've got a couple more iterations of RTX down the line, I wouldn't be surprised if people just stop supporting rasterization entirely, because ray tracing is pretty cool. So, all right, so that's it for today, guys. I'll see you guys on Thursday. Peace out.